And I'm taking attendance right now. I don't think I need avatar because I know you guys. Yeah, I know. Okay, thank you very much. All right, now that's for today's attendance. All right, let's just get started. Okay, so we are going to start today. Actually, it's 11:59. I shouldn't start. I'm meeting earlier. You just continue chatting. Wow. Still no time yet.
I'm your partner. Cool. Nice to meet you.
Yeah, it's just good for you. Confirm who's you working with, yeah? Because project one is already assigned, right? Let's begin with updates. So there are a few new updates since Tuesday, right? What is the new? What is not new? I cannot even tell. So right now, what's today? Today is Thursday 11. Okay. So there are a few things that you have to do. What is it? Oh. All right. Welcome, Daniel.
Hi.
Us. yeah, that's right. Yeah, let's mute all for a moment. So if you have questions, just unmute. Okay, so I'm muting your microphone right now, but if you have any questions, just unmute and just jump right in anytime, okay? No problem, all right? Okay, all right. So today is Thursday, February 11. Right now, what you're working on? You're working. Oh yeah, you have done quiz 2, of course, and then quiz 3 is assigned. Quiz 3 is due Thursday next week, 11 a.m. Quiz 3. Oh yeah, what kind of quiz is it? I don't know. And also homework assignment, Unit A1, this is due next Tuesday. Okay. So when you turn in homework, let's be very careful. You submit one PDF per problem, just like this. Separate PDF. Each PDF may possibly be multiple pages, that's fine, but still single PDF. Separated each for each program. The reason is I'm going to randomly choose a few programs out of those, grade it, and then put it back into the graded file folder so that you can see by yourself. Okay? Now, no matter how many times I repeat the same instructions in aero class, we still have like a few people never understand what to do. Too bad. They keep getting zeros. They keep getting zeros, and then some of them don't even realize they're getting zeros. which I don't even care at that moment, you know. I mean, you just flunk yourself away. You just don't listen, read, follow anything. Okay, anyways, so you're not one of those people, of course. So please be careful, okay? If you took my class, I mean it. Those are the files you need. So each worksheet, you just download or print out. Either way is fine, but keep the same file name. That's very simple. Then as you turn in like this, separate PDF file. You can possibly make it like multiple pages. That's fine. No problem. Okay. Any question about homework? Okay, too bad. This is flight mechanics, not the aero. Too bad. So this is due next Tuesday. You have plenty of time, and those are easy problems. No worries. Okay. And then hopefully Jordan is keeping up. You feel like?
I'm managing.
Yeah. Okay. You feel like you're keeping up. That's great. And so quiz 3, right? Well, quiz 3. What's the quiz 3? Let's take a look.
That looks very familiar.
Derive the airspeed equation 3.25. We're We're going to touch base with it today. So we're going to look at the airspeed equation 3.25 today, but you have to derive this equation. Of course, you need to go back to aerodynamics. Oh, of course, we did it. Yeah, we did it. Yeah, sure. We derived airspeed equation, compressible form of Bernoulli's equation. Do you remember that? Bernoulli's equation can come with a form, something called compressible form of Bernoulli's equation, aka energy equation. Do you remember those? Yes. So we are going to go back and take a look and derive this airspeed equation. You need to start all the way from compressible form of Bernoulli's equation applied to a pirostatic probe just like this. Okay. From AE317, the compressible form of Bernoulli's equation, often referred as energy equation, can be found by this. CPT, which is enthalpy, right? Well, anyway, CPT plus 1/2 V squared is equal to CPT 0. 0 stands for total pressure, which is stagnation point. Okay? So T0 is a total pressure at the stagnation point. Infinity is a free stream, of course. And then pressure P infinity can be sensed at the static port. Of course, this is pirostatic probe. Okay, you know that. And then subscript 0 means stagnation point. Infinity means the free stream. Cp is a specific heat under constant pressure. Cp is gamma R over gamma minus 1 if it's calorically perfect, ideal gas. Do you know those things? Remember those things? Of course, you know. Please spend some time do this problem. It's a fun time memory trip back to aerodynamics days.
Yay.
Of course. Of course, yes. All right. Any question here? So that's the update. Okay, not so bad. And then today we're going to look at this equation. So please just don't sleep away. We are going to talk about it. Okay. Of course, yes. So let's just pick up from page 8, Unit A2. Okay, so page 8 of Unit A2. Let's continue on a little bit more exercises of read off the data from NACA airfoil data charts. Example 3.8, let's calculate the maximum camber, location of maximum camber, and the maximum thickness of a NACA 2412 airfoil with a chord of 4 feet. Wait a minute, didn't I do that? It's kind of very similar to, well, it's almost the same problem. Okay, let's just do that. All right, so NACA 2412. Okay. Sorry, I need a grab. Sorry about that. Let me put the grabs. Okay. NACA, what? 2412. So first of all, maximum camber. Maximum camber. Maximum camber is the first digit, 2, right? Maximum camber is 2% of code, which is 0.08 foot. Okay, 2% of code. And what is location? Location, second digit 4, okay? So the location is a 40% code location. That's where the maximum camber is, location 40% code, which is location measured from leading edge 1.6 feet. That's the location of maximum camber. And maximum thickness, which is 12%, yes, that's right. Maximum thickness, 12% code. 12% is 0.48 feet. Okay, so very simple. NACA 2412. Sure, you know that. So once again, let's take a look at page here. NACA 4-digit. So first digit describing maximum camber in percent of code. Second digit, 1 digit describing the distance to the maximum camber location. measured from the leading edge in times 10% code. Last two digit is the maximum thickness, usually at the quarter code location. Okay. Maximum thickness at the quarter code location is called conventional design, like a 4-digit, 5-digit. Okay. So now I think kind of know those things. Example 3.9. Determine CLCD, CM quarter code, CMAC, alpha zero lift, CL max, and alpha star for NACA 2412 airfoil at the alpha equal to 12 degrees angle of attack. Assume Reynolds number 3 times 10 to 6. Let's just do that. So each person take a look at page 6, which is NACA 2412. Okay. Here we go. Oh, I'm going to zoom in. So this is NACA 2412 airfoil. All right. So there are multiple things we have to do. What is the, well, at the alpha equal to 12 degrees, what is the CLCD, CM quarter code? 12 degrees. It's right here.
1.42.
That's right. Well, this line right here. So 1 point, not quite 1.1. It's like what? Sorry, I lost it. Okay. Alpha equal to 12 degrees angle of attack. Okay. What's CL you got? 1.42. I got 1.4. Anybody else? 1.4, 1.4 something. Okay. 1.42 is fine, certainly. Okay. And CM quarter code. CM quarter code. Let's just take a look. CM quarter code at 12 degrees angle. Right here. This value. Let's be careful using this scale. Okay? Don't use the wrong scale. Negative. Negative 0.02-ish. I got negative 0.025. Negative 0.02 is fine, obviously. So this value right here, using this scale. Okay? Using that scale. Don't use the CL scale, though. That's a common mistake. People do that all the time. So CM quarter code, I got minus 0.025. If you get minus 0.02, that's okay. It's very difficult to read off accurately. So you just do your best to read off. So this actually gives you certain information here. You want to have CL alpha, lift curve slope. This is how much CL change happens over the change of alpha. So let's say typical choice is, in this case, you are going to pick up 8 degrees. 8 degrees? Why? Why 8? I have no clue why. Here. I'm going to fix my notes. Anyways. So in this case, okay, I'm going to, of course, choose 12 because it's 12. 12 is, you know, CL is 1.4. And what is alpha zero lift for this case? Somebody please tell me alpha zero lift. Negative 2, that's right. So negative 2 degrees is alpha zero lift. That's where the CL becomes 0, right? So this is a typical choice. Now you're talking about 12 degrees of angle of attack, and then this is alpha zero lift where you know CL becomes 0. So if you do this, what's the value here? 0.0. 1, 0.1, 0.1, okay. What's the unit per degree? This is CL alpha. Okay. This is CL alpha. Okay. So this is a rift curve slope out of the data set given. And also, if the CL is 1.4, which means this is alpha equal to 12 degrees, correspondingly, what is the drag coefficient? CD. CD equal to? Let's just read off. If the rift coefficient is 1.4, what is the corresponding CD? You are going to read off the value from drag forum. Let's take a look. So this is the drag forum. Now suppose if your CL is 1.4, 1.4 here, all the way here. What is the CD corresponding to it? Am I looking at the right Reynolds number? 3 times 10 to 6 circular data point. It's actually here, isn't it? What's the value?
0.017.
0.017. 0.017. Yeah, okay, good. So let's just find out. CD, I got 0.0173. I don't know what 3 comes in, but I said so. So CD is about 0.017. That's okay. I got 0.0173. This is what the textbook also says. You know, the professor at the Air Force Academy, right? So we just take that value. I don't know why, but. How do you read off 0.0173? Well, anyways. So 0.017-ish. This is a drag coefficient. And also, in the same token, if the CL is 1.4, what is the CMAC? Aerodynamic center moment coefficient, which is fairly constant value, isn't it? What's the value here? Once again, you're going to look at the table, chart on your right.
Negative 0.048.
0.048, 0.05. Okay.
The one time I wasn't going off to sig figs, and it was the 0.0173.
Yeah.
And now it's the opposite.
Oops, too bad.
Oh my God.
Well, that's a big points off, right? Like something like that. You front the exam, you get F kind of situation. No, I mean, don't worry about it. You can just do your best, read off the best value. Yeah, you know, this is like a 1950s hand prod. I mean, who can get the accurate result read out anyways?
You can't clearly.
Okay, so now interestingly, it says CM quarter code is not equal to CM aerodynamic center. What do you mean by that? That means the aerodynamic center is not equal to the quarter code, right? Well, that's why the aerodynamic center is listed different from quarter code. Let's take a look at the data set here. AC position is 0.239. It's not the 0.25. So AC is shifted slightly forward because of this case. Now, the reason is you have a thickness and also camber. So this is a fairly thick camber airfoil, right? This actually have a tendency to shift the aerodynamic center slightly forward. Okay, I think we talked about that in Aero 1, but it does. It's pretty close to quarter code, but it's not quite quarter code. Okay. Still, people say, hey, you know, it's quarter code, fairly close enough. So let's choose quarter code as aerodynamic center. You can do that. Okay, so this is the thickness plus camber effect of a fairly thick airfoil. Okay. Now, next thing is, what's that? What is alpha? Zero lift alpha stall. Yeah, okay. Well, you get that. Alpha zero lift. Of course, somebody's already said -2 degrees. That's right. This is not affected by Reynolds number at all. Okay. very constant value. And then CL max, of course, we are going to read off the maximum value for a given Reynolds number, which is something like I got 1.68, something like that. Did you get the same value? Maximum lift coefficient. 1.68. Oh yeah? Let's take a look. 1.68 is like this point. Right? Maximum CL. And then stall alpha. Yeah, stall alpha. Stall alpha. Well, it's about 16. How about that? Stall alpha. So about 16 degrees angle of attack, airplane stalls. I mean, this cross section stalls out. So alpha stall is about 16 degrees. Okay. All right. So any question here? So this is a very simple look at this NACA 2412 airfoil. Okay. Example 310. Calculate the lift and drag and pitch moment using the coefficients obtained in here. CL equals 1.4, CD equals 0.0173. Well, it's written here. How's that? That's why it's 0.0173. You see that? You see that? You know, there's a reason why I choose 0.0173. It's written here. It's written here. Anyway. Okay. Okay. So let's find out. Condition is, okay. Condition is we are going to assume standard sea level. Okay. So let's assume all right, standard sea level. And velocity v infinity is 100 feet per second. Here we go. So dynamic pressure of a free stream, 1/2 rho v square. So dynamic pressure is 1/2. A standard sea level density is 0.002377 slug cubic foot. So this is standard sea level air density, US customer unit. Airspeed 100 feet per second. This thing square. This is going to get you dynamic pressure of this flight condition 11.885 pound per feet square. This is dynamic pressure, and the conditions given. Conditions given. Is that right? Conditions given. What's the condition? Chord length 4 feet. What else? Wing area is given? No. Wing area is not given. What are you talking about? Chord length is given. Yes, chord length is given. Okay. Once again, I found an issue. Chord length is given. C equal to 4 feet. And then there's a massive information missing. Area S is equal to 200 feet square. Who actually said it? It's not given.
Where did that come
Where does that come from? I think it's coming from here, maybe. No.
from?
Where does that come from? No, nowhere. Okay, nowhere. So information missing. So please add your information. Wing area to 100 feet square. This is completely missing.
Cool.
Wing area. Chord length. You need to be given both. That's right. Something missing. Sorry about that. Because all of a sudden solution says wing area 200 feet square. Where does that come from? Nowhere. Okay, anyways. Sorry about that. Okay, so let, okay, chord length 4 feet given, and wing area S 200 feet square, which is not given. I give it to you right now. Okay? If so, what is the lift per unit span? Lift is CO, section lift coefficient, times dynamic pressure times area S, which is 1.4, 11.885 PSF, 200 feet square. So this is the lift force in pounds, okay? How about the drag? Drag is CD, QS. Once again, drag coefficient 0. What was that? Drag coefficient 0.0173 times Q 11.885 pound per feet square. Area 200 feet square. This is the drag. What about moment at the aerodynamic center, MAC? This is the CMAC times Q times S times C. CMAC was minus 0.05. Q is 11.885. PSF. Area is 200 feet square. Chord length 4 feet. Right. All right, so let's compute all. Okay, what is the lift and drag moment at the aerodynamic center?
Dr. H,
Go ahead.
I have a question. So
Yeah.
you said it's lift per unit span.
No, actually, this is 200 feet means,
I was gonna
that's right, not the unit span. It's actually lift. This thing is area S, which is 200 feet square. So this is essentially, if you create a chocolate bar wing using this cross section, how much lift you're going to get? That's right. And then whatever the wingspan given, wingspan is not given, but the wingspan is given, if you divide by wingspan, it's called lift per unit span. Okay. So this is essentially lift for this airfoil test. Test, isn't it? That's right. So this is a wind tunnel test, I believe. So this is a lift and drag and moment at the aerodynamic center. Let's get the value. So please be careful. This is additional information. How is that? Are you doing it? Okay, go ahead. Okay.
3,327.
3,327 pounds. Any confirmation?
Yeah.
3,327. Okay, how about the drag?
41.12 pounds.
41.112 pounds. Any confirmation?
Yes.
Okay. How about the moment at the aerodynamic center? It's a negative.
Negative 475.4.
475?
475.
475. 475? My answer should say about minus 401. Are you sure? What?
Yeah.
Minus what?
475.
475
Yeah.
Yep.
Per pound.
per pound? Really? I found another mistake from Air Force professor. Okay. All right, I need to fix my notes. Any confirmation, minus 475, right? Okay, okay, I trust you guys over those Air Force people.
Dangerous game to play.
Here we go. All right, so any question here? So this is very basic. Read off the chart using the chart value to determine certain things. Of course, you have to do that all the time. Now, the beauty of using X-Flyer 5S, okay? You're going to actually use the software, and the software computes all of those things for you, okay? And then you can actually design your own cross-section and then do some basic analysis based on the range of Reynolds number. You are going to accumulate all of those data sets, okay? All right, so next page, let's move on. So ICE-T, the complete story. So this means that we went through ICE-T airspeed conversion calibration process. I stands for indicated, C is a calibrated, E is equivalent, T is a true, and then oftentimes ground, ICE-TG, to complete. Now we looked at ICE-T or ICE-TG calibration conversion process only for less than 0.3 Mach number case, which is a Bernoulli's equation based airspeed equation. So now we are going to look at more than 0.3 Mach number. So this is a compressible Bernoulli. Okay, have you ever heard of it? Compressible form of a Bernoulli's equation. What is it? Please give me that equation. Energy equation. Yes, that's right. CPT plus 1/2 V squared is CPT0. That's what it is. This is called energy equation or compressible version of Bernoulli's equation. Based off of this equation, you can actually alternatively derive airspeed equation, which is airspeed equation more than 0.3 Mach number. Here we go. So this is it. This is it. This is it means I mean it. Because this is quiz 3. You are going to derive this equation. Can you do that? This is quiz 3. Can you get this equation by yourself? It's a quiz 3, which is due when? Next week, right? Or do you have questions? Or you just, oh yeah, I can do it and move on. Oh yeah? So you can do it, so I can move on.
No, I can't.
If you feel uncomfortable, you better stop me. Otherwise, you're going to screw up quiz 3.
There's one person in the class.
Okay, good. So I wouldn't blame you. So let's just take a look at how we do this. Okay? How we do this. I'm not going to do it, but I can take a look at how we do it. Wow, well, because it's a quiz, you have to figure it out somehow. So I'm going to take a look at the aerodynamics notes. Aerodynamics notes. Well, of course you can do it. I mean, you took my aero. Do you remember this unit A4? Do you remember unit A4? I hope. Well, do you have a unit A4 notes with you? I hope so, yes. If not, you can download it anytime.
Wait a minute.
Do you have it? Oh, that's good. I'm so proud of you. Oh, he's got notes. Here we go. Oh, that's a lifetime asset. 20 years from now, you're still using it, right? At some company like a Boeing, or you're still using it. Anyway, airspeed measurement in high speed. So obviously in aerodynamics, unit A4, we talked about airspeed measurement, of course, starting with less than 0.3 Mach number. Well, first of all, this is like a speed of sound. Speed of sound equation, we derived it. Okay? Speed of sound equation is coming from continuity plus Euler plus first law of thermodynamics plus isentropic flow plus calorically perfect ideal gas. Then A equal to square root of gamma RT. Do you remember that? Okay. I hope so. Yeah, okay. And then measurement of airspeed, of course, we're going to use what's this? I have no idea. Well, there's a bug in Microsoft Word these days. Equations always kind of keeps changing like this.
Hey, that's our quiz.
Oh, this is a quiz.
Wow.
Cool.
Yes. Yeah. So anyways, this is a pedostatic probe, right? And of course, if it's less than 0.3 Mach number, of course, this is the equation. Sure. But if it's more than 0.3 Mach number, of course, you are going to employ, yeah. Of course, this is less than 0.3 Mach number. This is the airplane we have, Cessna, yeah. We don't have to worry about changing density. It's always Bernoulli kind of equation. So now question is, if you go for higher than 0.3 Mach number, you cannot use Bernoulli. So what do? What do? You still use Bernoulli, but the different form of Bernoulli. This is energy equation, right? So this is compressible form of Bernoulli's equation. Compressible form of Bernoulli. AKA energy equation. So starting from this energy equation, you're going to apply energy equation just like you did in Bernoulli's equation, applying for this picture here. Applying for this picture here. So you're going to apply energy equation along this path called streamline. Okay? So right here is an infinity. Also, this is also infinity side pole. Right here is a point 0. Okay, so you're going to apply between infinity and 0 the energy equation, aka compressible form of Bernoulli. The result is, here we go, this is the result. Okay? So energy equation or compressible form of Bernoulli's equation basically tells you the relationship between the temperature between stagnation point and free stream is a function of what? Mach number. That's what it is. So free stream Mach number basically tells you the ratio between stagnation point and the free stream temperature. Temperature ratio comes in. Okay, it's a pure function of Mach number. And then if you apply this equation together with isentropic flow relations, you can come up with two more equations. One is, of course, if you take the ratio of the pressure between stagnation point and free stream, it's also a function of Mach number. And also you can do the same thing. Density between stagnation point and free stream, density ratio is also, of course, the Mach number. So this equation basically is the reason why less than 0.3 Mach number is called incompressible subsonic. In other words, if you take a look at Mach number plugged in 0.3 right here, what is the ratio? It's the change of less than, this a 5% change. In other words, 5% change or less, you can basically ignore that and consider it's incompressible subsonic. If you plug in 0.3 here, the change between stagnation point and free stream density is less than 5%. Okay, so that's the original argument of why less than 0.3 is incompressible subsonic. Do you remember those things? Okay, so starting from actually this equation, you are going to solve this equation for, so what is Mach number equal to? So you're going to solve Mach number equal to, and then knowing that Mach number is equal to B infinity over A infinity. So B infinity is equal to A infinity times Mach number. This is the airspeed. So airspeed equation is coming from this equation, next page. Okay? So starting from this equation, you're going to solve it for Mach number. There's so many. What's 1? This is M. Okay. So here we go. This is airspeed equation for more than 0.3 Mach number flow field. Do you feel like you can do it? Jordan? I hope. Do you have any question here?
Can we go back up to the Mach number page real quick?
Mach number page here.
I think it's like 3 or 4 pages up.
354 pages up.
It's where it defines M equals B over A.
M equal to B over A, yeah? Which page?
Keep going. There's a part I had a question about. I think it's this one.
This one.
A little bit more.
A little bit more.
Well, there's a spot where it is deriving the A,
A.
and it said that D rho dA was equal to 0, so you can cross it out as part of the derivation. And I wasn't. Oh, right there.
Oh, yeah.
Page. Yeah. So that the D rho dA on the right side
Yeah.
equals 0.
Yeah.
Why is it we can cross that out?
Because D rho is a small differential change of density. dA is a small differential change of speed of sound. Small differential change multiplied by another small differential change is a very, 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 very small differential change. So we are just going to ignore that.
Okay.
Yeah, that's why. Although you don't have to derive this though.
I
This
know.
is,
I was just.
yeah.
I've never taken any of these things, so I'm starting from very
Yeah.
beginning. So
Yeah,
I
yeah.
understand it all.
Okay. So this note is given to you, right? So you can look at it. Yeah. Okay. But this derivation is not the part of the quiz 3 at all.
I know.
So you shouldn't worry too much about this. It's
I know,
like
I'm
a
just
way
trying
too
to-
much sidetrack.
I'm just building a foundational knowledge.
Okay.
Because I don't understand any of it. So.
Yeah.
I pretty much have the quiz on this page right here.
That's pretty good. Yes, that's right. So that's a price list, right? Here we go. Good questions. Anybody else? So all of those error notes are given to you, okay, in this class. All right. And then I found so many errors, and especially disturbing to see like Microsoft Word is doing this kind of thing. I literally explode. Microsoft Word. I mean, why so buggy?
Yes.
You don't have to create this kind of bug. Anyways, it looks so like it looks so stupid. Anyway, it just changed the fonts and types and equations. It just drives me nuts, really. Drives me nuts. Problem is, I'm not paying any peanut for Microsoft these days. That's why I can't complain. Schools pays everything. I don't pay anything. I don't pay peanuts for Microsoft. You guys are, I think, part of the tuition, right? Too bad. Okay. Okay, so this is the airspeed equation, which is based on the compressible Bernoulli's equation. So that means this equation is applicable for more than 0.3, but still subsonic. Okay. So for the airplane flying subsonically but more than 0.3 Mach, whatever the airspeed indicator, the instrumentation is relying on this equation. So this is airspeed equation. So now this is indicated airspeed. Now, starting from this indicated airspeed, you're going to go through the exact same calibration process, okay? So starting from indicated, you're going to come up with calibrated airspeed. Of course, you're going to calibrate based on the position errors and all that. It's a pitot-static tube itself. Then you're going to get calibrated airspeed, BC. Okay. Now, one thing you noticed was the calibrated airspeed actually uses the standard suitable density and pressure right here, compared against indicated. Okay. So this is oftentimes called compressible subsonic calibrated airspeed, which is basically relying on standard suitable density pressure. Okay. Next step. All right. Next step is calibrated airspeed multiplied by F factor correction to come up with equivalent airspeed, VE. Remember that? F factor. F factor is going to be multiplied with the calibrated airspeed, come up with equivalent airspeed. Now, the big difference here is now pressure is now pressure at your flight condition, pressure at flight condition. The only thing is, suppose if the density of air is a standard suitable value, what would be the airspeed? It's called equivalent airspeed. Equivalent airspeed is usually the lowest value. And then this is airplane's force generating capability. In other words, if you are trying to fly airplane at the standard sea level, how fast you can go. Okay, so this is usually used for design indication, equivalent airspeed. The next step is, of course, okay. Yeah, that's right. So this is the F factor correction. That's right. So true airspeed is now you are going to multiply square root of density ratio between sea level to actual density of your flight altitude. This actually requires one more information, oftentimes called OAT, outside air temperature. If outside air temperature is given, you are going to compute actual flight density. And then if that information is given, you can determine true airspeed. Okay? So this is, like I said, ICE-T, indicated, calibrated, equivalent to true. And then if there's a crosswind, of course, you're going to convert it back into ground speed. Okay? If there's no crosswind, true airspeed is equal to ground speed. It's the same process. Okay? ICE-T, ICE-T-G. Also, another important thing, if you're flying more than 0.3 Mach number, this actually applies for X-Flyer 5. Suppose if your airplane flight condition is more than 0.3 Mach number, your software only computes if Mach number is less than 0.3. In other words, your panel method solver, X-Flyer 5, is based on the ideal flow, which is incompressible flow only. So whatever the calculated value needs to be corrected for higher Mach number. Okay, this is called compressibility correction. Friendograd. Friendograd compressibility correction. Okay. So lift coefficient result is given for less than 0.3 Mach number. This is going to be corrected. Using Mach number. If Mach number is more than 0.3. This is called compressibility correction. Okay. So NACA airfoil data, for example, that is the Reynolds number pretty low. That means it's less than 0.3 Mach number test anyways. It's a small wind tunnel, okay, low speed. So NACA airfoil data charts provide lift and drag moment information of low speed as the data is based on low speed wind tunnel tests. However, you oftentimes have this situation. In other words, you're talking about same exact Reynolds number as if you match up the Reynolds number data with NACA chart. However, your airplane is actually flying faster speed in higher altitude. How's that? That means, hey, Mach number is no longer less than 0.3, even though the Reynolds number matches up. There is a situation just like that. Suppose if that happens, what do? You are going to correct your data. In other words, you read off the CL, CD, CM code, all of those values read off from NACA chart need to be corrected for your higher Mach number. Okay? That is called Prandtl correction for lift and lift curve slope. You have to do that sometimes. Okay? So let's be careful. If you forget about this, your predicted performance is going to be very, very low, even though you are flying faster Mach number. Usually, airplane flying faster than 0.3 Mach number means that your performance is much, much better than you predicted. You missed all sorts of good stuff. And then you become overly pessimistic about your design of your airplane. Oh, our airplane is not so good, but in fact, it's actually a very good airplane. Could be. Okay? So almost always, Prandtl correction needs to be done if your designed airplane flight Mach number is more than 0.3, almost always it is, right? By the way, do you have any plan of what kind of airplane you want to design in this class? A category of airplane. Just curiosity. What kind of airplane do you want to design using software X-Flyer 5? Jessica has a very good idea. It's a biplane very heavy carrying airplane. So airplane that is probably, what's the span? 5.5 feet span, and how many soccer ball or something you have to carry?
So the plan is to carry one soccer ball about 18 pounds of steel plates.
18 pounds of steel plates plus soccer ball with a 5 feet span airplane. That's crazy. So that's why I'm going to go for biplane. That's what your plan is, right? Okay, so that is one design concept you already come up with. It's a competition. You can't change it. So other teams, do you have any idea of what kind of airplane we are curious about, interested in using this software? Anybody who wants to go like an insanely high speed, like a supersonic airplane? That's actually very challenging thing because most of the high speed computation Xflyer 5 cannot handle, so you have to do lots of hand calculation. If you are willing to do that, that's fine. If you're willing to do that, that's fine. I'm going to cover that anyways in this class. It's just lots of tons of hand calculation added onto Xflyer 5. Anybody who wants to do like a seaplane, flying boats and stuff, you know, the big thing is those boat sections cannot be covered by Xflyer 5. You have to add tons of hand calculation for that component. Again, you can do it, but so I think the easy choice is, well, just the airplane, middle speed, not so fast, not so slow, good size, maybe a radio control airplane I wish to build and then play with it kind of thing. With an electric motor this big, I mean, I actually have an airplane. I want to simulate it. So again, it's a time to start thinking about it. So this is a class focused on, let's use the software to design and analyze those kind of things. Go ahead.
Is it possible to design a variable geometry wing with Xflyer 5?
You have to deal with like two geometries. One is this wing, one is this wing. So you have to double your analysis. This is analysis A, analysis B, always double amount of workload.
But you're saying it's possible.
It's possible. I mean, nothing is impossible. If you're willing to do like a double amount of work, yes. Anybody else? And you have to check your teammates. You know, your teammate is like, no. Anybody else? So it's kind of time to start thinking about. You shouldn't probably go like a super huge, like a heavy lift tanker type of thing, like a C-17 replacement kind of design. Well, you can possibly do that. It's kind of difficult, and then you can never test it anyways, right? You can only test it in a smaller scale. Easy one is, suppose if you're into like a hobby, like a radio control airplane, you already have an airplane, and let's just analyze that airplane using this software. It's probably very easy, and you can always test it. Okay. So it's time to think about it, okay, as a team. Okay. All right, so let's move on. Okay, so next page. So this is the example that we are going to look at the NACA 2412. Again, NACA 2412 airfoil data chart is given, okay? Now, let's think about, you're using NACA 2412 airfoil. Now you're going to create a wing. 0.5 meter code and 2 meter span wing. This is the chocolate bar wing once again. Here we go. So 0.5 meter code and 2 meter span wing is being tested in a wind tunnel at standard sea level atmospheric condition with a test section velocity magnitude of 168 meters per second at an angle of attack 8 degrees. What is the airfoil's lift coefficient curve slope? How much lift is generating? One thing you instantly notice, what is it? Ring a bell by looking at this program. Uh-oh, wait a minute. Is this a, oh. What is something you stop and think? Eh?
Pretty fast. Yeah, it's fast.
168 meters per second is pretty fast. Do you think this is less than 0.3?
We can test it using the standard sea level atmosphere conditions.
Well, and we have to check the Mach number, but do you think this is less than 0.3? No way. No way. Okay, so this is actually Reynolds number may seems to match up with one of those data set, but Mach number is more than 0.3, so you cannot just use the data as is from the data chart. You have to correct it because the compressibility kicks in for this type of test. Okay, so let's just take a look at first thing first. Let's just check the Reynolds number. So Reynolds number of the test condition. Okay, so Reynolds number of test condition is rho times B times C over mu. Okay. Standard sea level density, 1.225 kilogram per cubic meters. The velocity is 168 meters per second, which is pretty high speed. Chord length, 0.5 meter. Viscosity, 0.00001789 kilogram per meter and second. If you compute the Reynolds number, this actually is 5 times 10 to what? 6. Yeah, 5 times 10 to 6 Reynolds number. So if you go back and take a look at NACA 2412 airfoil data, do you have such a Reynolds number data set? Yes, you do. Okay. So I'm going to quickly go back to NACA data chart once again. Here we go. So you're going to actually pick up this Reynolds number out of this chart here. 5 times 10 to 6, okay? So the Reynolds number matches up with one of those data sets. However, the Mach number is more than 0.3 in this case. Oops, that means whatever the data read off of this chart needs to be corrected due to the compressibility. That's what it is, okay? So let's just take a look at it. All right. So this is the Reynolds number. And then you can read off all the data using NACA 2412 airfoil chart. Of course, from the previous exercise, alpha 0 left, we do know, minus 2 degrees. And if alpha is 8 degrees, you can read off lift coefficient CL. I think we read off 1.05 from previous exercise, okay? So alpha 0 lift is given, actually read off from your data, CL 1.05 for alpha equal to 8 degrees. However, those need to be corrected, okay? And then out of here, you can even determine CL alpha, lift curve slope. This is delta CL over delta alpha, okay? Delta CL is, of course, 8 degrees to alpha 0 lift, which is minus 2 degrees. At the 8 degrees, CL is 1.05. Minus 2 degrees, of course, CL is 0. This is going to give you lift curve slope 0.105 per degree. This is the lift curve slope data. I can pick it up from this NACA 2412 data chart, okay? Problem. What is the test section Mach number? Let's just double check. You can check it, B infinity divided by A, speed of sound. Speed of sound at the standard sea level is 340.3 meters per second. I know that somehow. It's a standard sea level temperature based, square root gamma RT. So this is the speed of sound at standard sea level, 340.3 meters per second. And then test section is 168 meters per second airspeed. So what is the Mach number? This is actually 0.49. Oh my goodness. This is more than 0.3. then you go panic and say, whoa, whoa, no, 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 we cannot use Bernoulli's equation anymore. Here we go. Not only that, whatever the data you read off from this chart needs to be corrected. Of course, you cannot use the data as it is. So let's just correct it. Okay? So NACA 2412 data needs to be corrected. For compressibility. This is called Prandtl compressibility correction. Now, your software XFly 5 has the checkbox, right? Checkbox says, what's your Mach number? You just type in. If you checkbox and type in your Mach number, it is going to automatically turn on this equation, Prandtl correction. Okay? All right, so be careful about that. Suppose if you are designing your airplane more than 0.3 Mach number, you have to checkbox and put your Mach number in it. Turn on Prandtl correction equation. So you're going to correct CL. So CL is going to be corrected, whatever the CL value for incompressible subsonic divided by 1 minus m infinity squared. So suppose you are going to get 1.05 alpha equal to 8 degrees, right? This is not going to be the same value. 1 minus Mach number 0.49 squared. This is going to be actually 1.2. Whoa, it's a higher lift coefficient. Of course, your airplane is flying faster. You are generating more lift coefficient. Yes, it's better, of course. How about CL alpha, lift curve slope? CL alpha is 0.105, okay. Same here, CL alpha of Mach number 0. In other words, this one, 0.105, also needs to be corrected. 1 minus m infinity square, okay. So 0.105 per degree, this is lift curve slope. However, since you're flying faster speed, this is, as a matter of fact, 0.12 per degree. Oh, much better. Yes, that's right. So overall, your airplane performance is much, much better. Okay? So now the question is, let's just recalculate the dynamic pressure Q. Q is equal to 1/2 rho v square. So this is 1/2, and again, standard sea level 1.225 kilogram per cubic meters. You are now flying 168 meters per second. So this is 17,287 Newton per meter square. So this is the Q, dynamic pressure. Wing area is B times C, wingspan times chord length. So let's just compute 2 meter times 0.5 meter. So wing area is 1 meter squared. That's right. So how much lift now you are producing? Lift is equal to CL times Q times S. That's right. CL is 1.2. Q is 17,287 Newton per meter square. Area is 1 meter square. So what is the lift you are actually producing.
20,744.
20,700.
44.
41.
What?
40 what? 40. 20,740.
44.
44 Newton. Any confirmation?
Yeah.
20,744 Newton. So if you compare this value against previous result is like what? Lift was, oh, I can't even compare, sorry about that. Okay, sorry. So this is a lift. There's no relationship with the previous exam. I thought Air Force guys are better than this, but anyway, sorry about that. So this is, suppose you testing in a high-speed wind tunnel, which is more than 0.3 Mach number, even though you can match up Reynolds number, but you have to do compressibility correction. Okay, so this is one of those things. All right. Oh. Let's get into boundary layer today also, interestingly. Yeah, that's right, too bad. You still have time. So boundary layer equations. I'm going to introduce you something called Brazier's solution, flat plate. Have you ever heard of it? Brazier's flat plate boundary layer solution. Okay. So obviously the X-5 is a panel method. Panel method, okay. Panel method really means that you're going to solve it without looking at viscosity. So the solution is all implicit solution. So if you want to actually incorporate your boundary layer flow over the surface, in other words, your flow starts with laminar transition to turbulent and then somehow separates. You are going to add a boundary layer model on top of it. So there's a checkbox once again, okay, in your X-5 software. You have a checkbox, check mark it, and then boundary layer transition criteria increase equal to 9. That means you're going to sort of natural transition, flow field from laminar to turbulent. You can actually avoid the transition, or you can actually force transition at certain location by putting like a tripwire type of thing. So you can control surface boundary layer in your software. So this is the model, okay? Boundary layer equations. Boundary layer equation is based on the flat plate, okay? Let's just take a look at the example A24. Okay. This is the boundary layer flat plate solution, Brazier's solution. Suppose if you are given completely laminar turbulent, laminar boundary layer, sorry for that. Laminar boundary layer. This is the equation of the thickness of the laminar boundary layer. This is the equation of the thickness of the turbulent boundary layer. This is the skin friction drag coefficient due to the formulation of boundary layer on the surface. So this skin friction coefficient depends on the type of the flow, laminar or turbulent, either way. So this is all flat plate boundary layer flow solution, laminar or turbulent. I think if you took AR2, you did this. Are you taking it right now?
Took it last semester.
Took it last semester. So this is the AR2 subject. Yeah. Okay. Anyways, so software X-5 uses this equation-based flat plate boundary layer with the curved surface. Curved surface actually serves for pressure gradient. So if you have a completely flat plate, it's a pressure gradient 0. You're not going to accelerate, decelerate. But if you introduce a curve, it's basically pressure gradient introduced. It's a shape. Okay. So again, I'm not going to cover the details of those, but there is a model of a boundary layer model, which is the solution associated with. So if you take a look at example here, okay. So this is a thin flat plate. Once again, chocolate bar wing. A thin flat plate with a 2-meter code, 10-meter wingspan is being tested in a wind tunnel in standard sea level atmospheric condition with a test section velocity magnitude of 70 meters per second at the 0 degrees angle of attack, assuming the critical Reynolds number, 500,000, and no disturbances to the airflow due to the model mounting and test apparatus. Estimate the total skin friction drag on the plate. This critical Reynolds number is essentially transition point. When the Reynolds number hits 500,000, flow becomes turbulent from laminar. So right here, transition point. So this X critical can be determined from this Reynolds number. Okay. So as long as the flow is laminar, starting from leading edge, you're going to pick up the equation here, laminar equation. And then once you have transition, flow becomes turbulent. Now you are going to use the turbulent equation. So you're going to switch back and forth, laminar to turbulent skin friction coefficient equation to determine total skin friction drag. Okay. Here we go. So this is a step-by-step interesting process. So first of all, you are going to determine the predicted transition point based on the given critical Reynolds number. Critical Reynolds number is given by 500,000 right here. So this actually determined Reynolds number at the trailing edge and also critical location X crit. So you have a transition 0.10431 meter. This is where the transition happens. You're going to compute that. And then second thing is you're going to calculate the drag for the combined area A plus B. 5 more minutes. Combined area A plus B, assuming that the flow is completely turbulent. What do you mean by that? You are going to, this is a plate. Okay. So this is area A, this is area B, this is a leading edge, here's a trailing edge. So first of all, you are going to compute, suppose if everything is turbulent, what is the drag? Okay, so this is step 2. And step 3, calculate the drag for the area B only. So that means this is area A, this is area B. Calculate the drag for the area B only. The flow is turbulent. To do this, calculate the drag for the area A, and then subtract this from the result of 2. This is the result. Suppose A and B are both turbulent. How much drag do you have? Suppose if A is a turbulent, you subtract this portion, what kind of result are you going to get? If you subtract this portion, this is A and B. This is entirely turbulent. If you subtract from here to here, what you have is this. Okay? Calculate the drag for the area A only if the flow is laminar. That means this is area A, this is area B. This is a laminar flow. So those two added together is going to be the entire picture. Does it make sense? Okay, so that's the strategy. So entire picture is, this is laminar. And then transition happens here. This is the total picture. So you're going to determine how much drag do you have if you have a situation like this by step-by-step process. Okay, compute the turbulent drag coefficient, if entirely turbulent. You subtract portion A, leaving portion B as a turbulent flow, and then add the portion A being laminar, add it together, it's going to be an entire picture of drag coefficient. This is the process. Okay, you have to do the exact same thing to solve your homework assignment. Okay, anyways. So any question here? So let's just stop here today. So next class, we are going to move on to Unit B, Unit B1, okay? If you have any question, just let me know, and also you get started for your project, phase 1A, okay? All right, people online, do you have any questions? Doing good?
Doing good.
All right, have a wonderful day, and then see you guys back on Tuesday.